So the last speaker of this session is Nishant Chandran. Nishant Chandran got his PhD from sunny California, from the University of California at Los Angeles. He worked in the famous AT&T Bell Labs for many years, and he now works at Microsoft Research in Bangalore. His area of expertise in computer science, and I will say what that means in a second, is theory and cryptography. When he's not doing computer science, he's quite a well-known violinist who has played in many, many venues and played with many famous people. And you can, if you Google him, you'll see violin clips of him. So I'll let Nishant actually talk about computer science.
Thank you, Chandu, for the introduction. I'll start the talk with a disclaimer that will go one better than Mati, that I do not work in AI or ML, and I don't work in systems also. And I did tell Chandu this as well, but what I can tell you is that cryptography research has got to an exciting point where there's been advancements up to the point where I think it could have very useful consequences to AI and machine learning as well. And for those useful consequences to bear fruit, I think a lot of systems work is also needed. So with that, I'll start my talk. My talk is going to be about something called as private multi-party AI. There are a couple of terms over there, but oh, I didn't get the clicker from somewhere. Oh, this is the one. Okay, all right. Thanks. So it's about private multi-party AI. There are a bunch of terms over there. I'll define all of them. All right. So before we talk about private multi-party AI, let's take out one of those words and just talk about what private AI is. Private AI, I'd like to think about it as the following problem. Let's say you have a cloud provider like Azure. You have a customer. This customer has a whole bunch of data, and as Chandu mentioned in his introduction, quite often this data might also be private and sensitive. Now the customer would like to send across this private data to Azure. Azure has very nice machine learning algorithms, so the customer would like to execute these nice ML algorithms on the private data, except that the customer would like the guarantee, Azure should not learn anything about my private data because this is sensitive information, it could be health records and so on. So this is the problem of private AI, and how do I solve this problem? So there are many ways researchers have considered to solve the problem of private AI. I'll highlight two broad themes over here. The first one is to take a hardware-based approach to the problem, otherwise known as trusted enclaves, where I'll assume that there are certain hardware regions or components that do not fall under the purview of an adversary, and then based on that, I will design systems. The other view is a pure software-only view, where more of my expertise lies in, which is a cryptographic view, where we say, look, we are not willing to trust that any hardware is completely secure, but we trust in mathematics. And so we'd like to design cryptographic protocols and encryption schemes such that no matter what an attacker does, he'll not be able to learn something about your private data. And that's in this context, homomorphic encryption is one such technique that can solve this problem. Okay, so let me just illustrate how one could potentially solve private AI using both these methods, and they both have a very, very similar flavor to it architecturally. So in the SGX context, we have Azure that additionally also has SGX machine sitting over there. Now, the hope is that now you can encrypt your private data with a key that's only known to this trusted enclave over here. So the customer can share a private key with the SGX enclave, and this key is not known to anybody else. It's not known to Azure as well. And what can happen is that the customer can encrypt his or her private data with that SGX key, send it across to Azure, and now the SGX component can decrypt all the data because it has the private key, and it can execute the ML algorithm on the data, and return back the responses to the customer all in encrypted format. Okay? And you get security because Azure does not learn anything about the data since it does not possess this SGX key. So the SGX key is something that's known only to this trusted component over here. All right, so that's how you could solve the problem of private AI at a very, very high level. I'm not getting into a lot of details over here, using trusted enclaves or Intel SGX. Now, on the software side, using techniques like homomorphic encryption, which is a powerful kind of encryption. Most of you may have heard about regular public key encryption, where if I know your public key, I can encrypt a piece of data and send it across to you, and you can decrypt it. But with most regular encryption schemes, once I encrypt the data is pretty much useless. The only thing you can do is to decrypt the data and then learn what it contains. Homomorphic encryption allows this fascinating thing that I can encrypt data and give you a ciphertext, but what you can do is, without knowing anything about the underlying plain text, you can run computations to get encrypted versions of the computation, right? So if I had an encryption of M, I could compute an encryption of M plus 1. Without knowing what M was, I could get an encryption of M plus 1, right? And fully homomorphic encryption in general allows doing something like this for arbitrary functions. So if I have such a gadget available with me, then what the customer can do in this scenario is to encrypt his or her private data with an FHE public key or a fully homomorphic encryption public key, the private key of which is known only to the customer, right? So Azure doesn't know this private key. And now, since homomorphic encryptions have this nice property that you can compute over encrypted data, you can run a machine learning algorithm on that encrypted data to get encrypted outputs. Okay? And security follows from the fact that Azure does not know the fully homomorphic encryption private key, and only the customer knows it. Okay? So these are the two broad ways in which one can try and approach the problem of private AI. Now, naturally, one might ask, which approach is better? Should I take a hardware approach? Should I take a software approach? And I'll warn you that this question is not at all easy to answer. It's a highly complex question. I will shed a little bit of light about the pros and cons of these various techniques when I discuss private multi-party AI, but still this is a very complex question that if I wanted to give a comprehensive answer to this, that would be a separate talk. All right, so now that we've seen what private AI is, let us get to what private multi-party AI is. Now, private multi-party AI is a specific case of the problem of collaborative computation. And in the problem of collaborative computation, you have multiple parties over here. So in my example over here, we have 5 parties. And all these parties have private inputs. Right? In the previous context, we saw only one party that had private inputs, and you wanted to do some computation. Here, now you've generalized the problem. You have 5 participants, and each of them have some private input. Now, they jointly want to run some computation on their private inputs. Okay? And their goal is that they don't want to share their private inputs with one another. So they want to keep their private inputs hidden from other parties. Right? And this is what is collaborative computation. Okay. Now, if these participants had a trusted third party available with them, then this problem is fairly easy to solve. All of them send their inputs to this trusted third party. This trusted third party computes whatever function that they wanted to compute, because he has all the inputs with him. Right? And then he returns the output to each of these parties. Right? And pictorially, it's clear that these parties have not shared their private inputs with any other party. They have only done so with this trusted third party. Everything is fine. But naturally, we'd like to ask the question, can the trusted third party be completely removed? We do not want to trust anybody. Can we still ensure that you can solve the problem of this collaborative computation? Okay. Now, again, there are multiple approaches to collaborative computation, and you may have observed that the previous 2 techniques that I spoke about, both the hardware-based SGX solution as well as the homomorphic encryption, can also be used to solve the problem of collaborative computation. In collaborative computation, there is another cryptographic technique that one can use, And that is known as the technique of secure multi-party computation. I'll talk about these three things in a little bit more detail next. Okay, so just to recap, if I wanted to use one of the first two approaches to solve collaborative computation, that is either the SGX approach or the FHE approach, how would I go about doing this? So in the SGX approach, we have these multiple participants, and then we have an SGX component that's a trusted enclave with which these participants can communicate with. So now what these participants can do is that they can encrypt their respective inputs with the key that's known only to this SGX component. They can send across their inputs to that SGX component. The SGX can decrypt all the inputs, run the computation in the clear within the trusted enclave, and then it can encrypt the output and send it back to the appropriate participants. Okay? So pictorially, it's fairly clear how you can make use of Intel SGX or a trusted enclave in order to solve this problem of collaborative computation. Similarly, if I wanted to use fully homomorphic encryption to solve this problem, parties can send their encrypted inputs to the untrusted environment. And in fully homomorphic encryption, as I said, you're doing computation, but you really don't know what's happening inside. It's like you're blindfolded, but still you can make use of your hands and do some computation. Okay? So the compute can take place over these encrypted inputs to generate an encrypted output. So you get encryption of the function output on all these inputs. And then you can send the encrypted outputs back to each of these parties, except that I told you that nobody must possess this private key. So who has this, the key of the fully homomorphic encryption scheme? In the single party setting, it was fairly obvious there was one participant. He or she generated the public key private key pair. Over here, which is the participants that generates the public key private key pair? It's a little bit more complex, but it turns out that parties can run a protocol to decrypt the result. I'll not say anything more about that. All right. That brings me to the last part of how you can solve this problem, which is actually the main focus of my work and this talk as well, the technique of secure multi-party computation. In secure multi-party computation, participants actually just directly interact with each other. Okay? So they have their private inputs, but they're going to be directly talking to each other and interacting with each other. And computation is performed through an interactive protocol between these parties. So if I want to compute something, I run some computation, exchange some messages, run some more computation, and so on and so forth. Okay? And I can ensure that the outputs are revealed by the protocol to whichever party must learn it. Okay? So this is something that cryptographers have studied from the early 80s, but today it's actually getting to a point where it's far more realistic than what it was even 5 years ago. All right, so just to compare and contrast a little bit the various approaches to collaborative computation, if I wanted to use an SGX or a trusted enclave to solve the problem of collaborative computation, here are a few properties they have. First of all, they are taking a hardware dependency, which is a bit unfortunate, but you need to assume trusted hardware over here. The second thing that, that comes about is that since you are decrypting, inherently you are decrypting ciphertext to get the real values and doing computation on the clear text values, it makes you susceptible to side channel attacks. By that, what I mean is how frequently you access some particular data, how long it took for you to do some computation, and so on and so forth. That can reveal information about the plain text data that you're working with, because the compute itself is taking place inherently on clear text data. Okay? So that's why it does not protect against these kinds of side channel leakages. So that's a bit of a problem with those solutions. On the other hand, the cryptographic assumption that you have to work with is very nice. It's standardized regular AES or public key cryptography that you have to work with, and that's always fantastic to do that. The performance of these protocols are fairly excellent. I mean, there's been a lot of work even at Microsoft Research where people have tried to run some of these neural network algorithms within SGX enclaves, and the performance has been quite good. With regards to programmability, if I have a program today that executes in the clear text and I want to run it within the SGX enclave, how do I do that? There is a little bit of work that needs to be done in order to make sure that those programs can run within the enclave, but it's not terrible. It also comes with certain other nice properties like verifiability, in that if I want a correctness guarantee that my computation was done correctly, I can get that from this SGX component. And it's also the case that one entity does the computation, because everyone is sending their inputs to one entity, and that one entity is doing the computation. All right. With fully homomorphic encryption, the picture is a little bit different. It's nice that you're not taking a hardware dependency. It's nice that you can have complete side channel protection, because you're never actually doing computation over clear data. You're always doing it only over encrypted data. On the other hand, the cryptographic hardness assumption that you need to make is a class of assumptions which fall under the lattice-based assumptions, which are not standardized today. The NIST does not provide guidelines on what parameters to pick. For example, if I wanted to use RSA or elliptic curve cryptography, NIST tells me what are the recommended parameters to use. There are no such recommendations from NIST today for these lattice assumptions, primarily because the attack frequency on these assumptions is far more frequent than on RSA or something like that. You may have some algorithm that brings down the breaking complexity of a lattice-based assumption a little bit every year or so, and then you have to refactor and change all the parameters as well. So that's a little bit of an issue with lattice assumptions. The performance is at best mediocre. It does take a lot of work to get these protocols to execute over encrypted data. Even in terms of programmability, one needs to take the clear text execution and then convert it into these complex algorithms that will run over these lattices and so on if I want to run the same algorithm. Verifiability, again, is not something that's easy to provide with fully homomorphic encryption, although we could try and get it. On the other hand, compute is nice. It's only one entity needs to do the computation. It's heavy-duty computation, but only one entity needs to do the computation. All right. So how does secure multi-party computation feature in all these, and how does it do on all these parameters? It's nice that there's no hardware dependency. You again get complete side channel protection because you never do computation on clear text data. The good thing is that it's completely based on standardized crypto assumptions, standardized AES, standardized elliptic curve cryptography, and so on and so forth. The performance, as we can see, is somewhere in between these two. It's good, it's getting better. It's between SGX and FHE. The programmability we'll talk about today a little bit is that we are taking significant steps into making secure multi-party computation easy to use. Anybody who's not even a cryptographer can today try and use secure multi-party computation. That's where we are getting. Verifiability can be obtained, but it's a bit costly. And finally, even though the compute is not as heavy as what needs to be done for fully homomorphic encryption, there is compute that needs to be done, and all participants need to be involved in the computation. And so that might be a drawback depending on the scenario. Okay, so this is how the landscape looks today. And the rest of the talk, about 7 minutes or so that I have remaining, I'll give you a brief overview of some of my work in this area and where we are in the field of secure multi-party computation. All right, just before I do that, let me paint a few scenarios where 2PC or multi-party computation is very, very natural. The first scenario is that of secure inference. And here, let's say that Azure has an ML classifier for disease, and it could be a respiratory disease or something like that. And let's say this classifier is IP, and therefore Azure does not want to share this classifier with any other entity. On the other hand, we have Bob, who has a medical report. It could be genomic data or any regular medical report, and he wants to learn a diagnosis without revealing his private reports. Right? It's sensitive information. He does not want to send across his medical data to Azure. So how can they solve this problem? This is a natural case of secure two-party computation, where these are the two parties that are involved, Azure and Bob, and they can execute a two-party computation protocol to compute the function on their private inputs. What is this function and what are their private inputs? The function over here is the classifier structure. For example, is it a linear classifier? Is it a DNN or a CNN or so on? X1 and X2. X1 is an input provided by Azure, which are the weights of the learned model. It has already trained a model, and so it has the weights of this trained model. And that's private input that Azure feeds in. And the input data point is X2, which is fed in by Bob. Okay? And secure two-party computation says that you can execute a protocol, and you can have the guarantee that Bob only learns the classifier output on the input point, and Azure learns nothing about Bob's input. Okay? Another scenario is that of secure training. And in this, you have multiple hospitals who have patient records that they do not want to share with each other. And these data points can be partitioned however you want, horizontally or vertically or whatever, we don't care. And now they want to run a training algorithm over their joint data without revealing the data to one another. Okay? And the final trained model can either be revealed to everyone, or it can be kept hidden and used only for prediction. Okay? If it is kept hidden and used only for prediction, then we have the scenario where finally they've run training, but none of them know the model, and then you have a customer, Bob, who comes with an input data on which he wants to learn what the output is, and he can interact with these hospitals to learn just the output, and no one learns anything about it. Right? So the model can be kept hidden for the lifetime of the system. All right, so how do you realize MPC in practice? This is the requirement that we'd like to have. If you're looking at machine learning today, most of the algorithms are written in a high-level framework like TensorFlow or CNTK or PyTorch or something like that. And what we'd like is, on the other hand, we'd like to be able to get protocols to execute these functions, right? Because I said MPC is a protocol between parties, so we'd like to get a protocol. So ideally, we'd like to write TensorFlow code and have a compiler that will automatically give us these protocols, right? Okay, so I'll break the suspense and say that's exactly what we can do today. You can write TensorFlow code, compile it, and you get secure computation protocols. Okay, our workflow roughly goes as follows. We go from TensorFlow to a C-like language and finally compile to our secure computation protocols. The first step is to convert TensorFlow into code that's quote-unquote crypto-compatible. There are a few security things that need to be kept in mind when you are working with cryptography. You need to ensure that the crypto code does not contain unbounded while loops and those kinds of things for various security reasons. But in a nutshell, what we do is we are able to compile TensorFlow code into something that's crypto-compatible. And so far, we have made progress on this front on secure inference, and I can talk offline about the challenges we are facing in taking everything to training, but it can be done. All right, so how does source code look like? As I promised, it's exactly TensorFlow code. You can write regular TensorFlow code, compile it, and you get secure computation protocols. So anyone who works in machine learning wants to see how their algorithm can be made private or secure, can write only TensorFlow code, nothing else, and then our compiler can give them a secure computation protocol for the same task. All right, the second part is where things get quite complex. Even though you have a C-like language where you can write these, the functionality that you want to compute, the problem is that the type of crypto protocol that you need to use to compute various functions are drastically different. For example, if I need to do something like a matrix multiplication, the type of crypto I need is very different from if I wanted to compute a ReLU. And the best thing to do, in fact, is to piece together these protocols. Use one protocol for matrix multiplication, use a completely different protocol for ReLU, and then write these interconversion protocols so that they are all compatible, right? And so this is a real mess if you don't know what you're doing, if you don't know which is the best protocol for which kind of compute. The good thing is our compiler takes care of all that for you. You don't need to know anything. It automatically figures out which is the best protocol for the type of computation that you're writing, splits the program into appropriate segments, and takes care of everything automatically. All right. Yeah, I'll skip this part. This is just how intermediary code for us looks like. This is a paper joint with Divya Gupta, Asim Rastogi, Rahul Sharma, and Shardul Tripathi, all of whom are, except Shardul, who was an intern, all of them are at Microsoft Research in India. All right. Finally, you need a cryptographic backend. And here's where a lot of the crypto meat is. You need to construct secure protocols, keeping in mind various considerations such as communication, round complexity, and so on and so forth. These protocols are quite heavy on the communication front, on the round complexity front, and so on. So you need to be very careful about how you design these protocols in order to minimize all this, and some of our work joint with an intern, Samir, is in coming up with better neural network protocols for this task. As a side note, there's a company called Dropout Labs that also has something similar, and they have recently, we just learned that they've been using our cryptographic protocols as their cryptographic backend as well, again, to build something like this where you can have TensorFlow compiling to secure computation protocols. All right, I don't have time remaining, but what I'd like to say in the remaining time is that performance of these protocols are okay. They are not fabulous. For inference, it's not so bad. On small data sets, things are of the order of milliseconds. It's all right. If I'm looking at neural network inference, it takes a couple of seconds for networks that work on say, MNIST data and so on. So there is a bit of compute and communication that needs to be optimized, but performance is getting there. So if I look at the multi-party scenario where I have 3 parties and I want to do some sort of prediction or training, we can do it in order of milliseconds, which is a lot better. And these are orders of magnitude better than prior work in this area, which is what I'd like to point out over here. Similarly, for training, we can do a whole bunch of tasks just because it's easy for us to write the functionality and get out crypto code for the same thing. Writing benchmarks is extremely easy today. And just to compare with clear text, we do have roughly 100x overhead over clear text data. But this is already like orders of magnitude better than the prior work. It's also heavily unoptimized code. The code that we are comparing with, which is the TensorFlow code, is fairly optimized and so on. But this is unoptimized, and there's a lot of potential for communication optimization, compute optimization, and so on that we have not yet started exploring to be thrown at this problem. Okay, so with that, I'll conclude and just say that MPC provides a nice software-only solution to private multi-party AI. The good thing is that it's based on well-studied, standardized mathematical assumptions. There is hardness of factoring or elliptic curve cryptography or AES. Those kinds of assumptions are what they make. They provide complete resilience to all types of side channel attacks. The performance is improving as we speak. Programmability is something that we have really focused on, trying to get things working over there. You can write TensorFlow code and directly get secure computation protocols. The performance is something that we are working on. It's an ongoing process. All right, thanks.
We are running slightly over time, but we can squeeze in a question or two if there are any. Okay, in which case, I'd like to ask you a question, if I may. What techniques do you use to make this thing faster? And what can other disciplines of computer science do to make that go faster? Is it compilers? Is it hardware?
So,
yeah.
So most of the techniques, newer techniques that we have developed is fairly simple number theory. There's nothing very complex going on over there. These protocols are fairly communication intensive. So you have to typically communicate something close, like some factor of your data size. And so if we are limited by how the speeds of the network that we are working with, and that is actually a fairly large bottleneck that we're dealing with. So right now, these performance numbers are on vanilla hardware, nothing large. Communications, I think something like 650 Mbps or something like that was the bandwidth that we get. And if we can optimize all that and get better network out of it, that would be fantastic. In terms of compute, it's only very, very simple integer arithmetic that we are doing.
Got it. So if you situate all your multi-parties or co-locate all your multi-parties, say using secure enclaves in one data center, how much, speculate how much better it would get?
What sort of bandwidth would you get out of it?
Moti, how much bandwidth can you give?
On Moti's hardware, maybe it will do phenomenally well, I don't know. Yeah, so
between 40 and 400 gigs, let's say. He provides 400. Normal people get 40.
If I had to just speculate, I would say at least a 5x improvement.
So from 118, it can go to...
Potentially. Because there's a lot of optimization need to be done on the compute side of this. For example, matmul is something that we just picked up, regular libraries that we use, and it's not optimized to death, and those kinds of things are not being done. But the good thing about the protocols that we have is they are not doing something very different from regular clear text compute. It's just that they have to do it more number of times and so on, but it's not that matrix multiplication gets converted to some group exponentiation or something like that and just change the flavor of the computation. Very much similar kind of compute that you have to do, just a lot more of it, and then you have this communication that's going on. And latency also is an issue because you're also paying round trip. So if that also is not an issue, then a lot of these timings can be much, much faster.
Anyway, my clock is telling me that we are out of time. Thank you very much.
Thank you.